Chemistry 3101. This is chapter 10, where we're going to deal with radical reactions. And if you go back to your general chemistry days, you would have been introduced to the concept of radicals or unpaired electrons in molecules like nitrogen monoxide. When you draw the Lewis structure of NO, you have an incomplete octet on the nitrogen. Right, you see that the nitrogen, maybe I could clear this double bond up, but you see that the nitrogen here is surrounded by 1, 2, 3, 4, 5, 6, 7 electrons, and so it has an incomplete octet. So that's where you would have seen radicals in general chemistry 1. Also, if you looked at the structure of things like NO2, NO2 is also a radical which dimerizes to give you N2O4. Anyhow, that's neither here nor there, but the whole idea is that when we have an unpaired electron, that is a radical, okay, unpaired electrons. All right, well, a bond can be broken in a couple of different ways. We can break bonds what are called heterolytically, and that's when we break them to form ions. An example that's shown here, if we break the bond between X and Y, we form a cation and an anion. That is heterolytic bond cleavage. However, homolytic bond cleavage is when we split the bond and we give one electron to each atom in order to form a pair of radicals. And so you see a big difference between these two reactions, not only in the formation of ions versus radicals, but we see that right here when we do the heterolytic bond cleavage that we have the movement of 2 electrons as represented by our double barbed arrow. And here we have 2 arrows that each represent the movement of 1 electron. And for that, we use what's called a fishhook arrow. When you looked at the table of bond dissociation energies, so when you look at a table of bond dissociation energies, which you would have used in general chemistry, and we also used them in chapter 6, we looked at a whole table of bond dissociation energies. Those bond dissociation energies that we looked at in chapter 6 came from homolytic bond cleavages, so breaking bonds homolytically. Well, let's get into those arrows a little more, because these fishhook arrows are going to be very important for us in this chapter. It's important that you know the difference between the double barbed arrow and the single barbed arrow that we oftentimes call a fishhook arrow. Right? All of these double barbed arrows that we've used in resonance structures and in mechanisms like SN1, SN2, E1, E2, etc., those arrows show the movement of 2 electrons, right? There's 2 electrons moving here. However, when we have the single barbed arrow, that shows the movement of 1 electron. So if we take a close look at this mechanism here, we have a single barbed arrow here and another one here. And since we know that there are 2 electrons in the bond, each atom, the X and the Y, are both going to get 1 unpaired electron to form a pair of radicals. All right, that's kind of an introduction into the concept of how we make radicals through the homolytic bond cleavage and what a fishhook arrow is. So these are things you need to be aware of. Well, now let's talk about the structure of a radical. What does a radical actually look like? Well, if we go back in our chemistry days to when we first learned about carbocations and carbanions, we said that the molecular geometry of a carbocation, which is an sp2 hybridized carbon, is trigonal planar, right? It is totally flat. And that's why we have this kind of planar arrangement here, is to show you that this is flat, or again, planar. Now, if we look at a carbanion, we have a lone pair in that extra sp3 orbital. So we have 3 sigma bonds and 1 lone pair. And we say that that carbon is trigonal pyramidal in terms of its molecular geometry, right? Both of these are molecular geometries, right? This is molecular geometry. Of course, the electron geometry here is still tetrahedral because electron geometry considers bonds and lone pairs. However, when we're discussing molecular geometry, we're only considering bonds, and so we have the trigonal pyramidal carbon. So these are things that you need to be aware of, right? You have to know that a carbocation is planar, trigonal planar, and you have to know that a carbanion is trigonal pyramidal. Well, where would a radical fit? Because a radical is somewhere in between these two, isn't it? It's not a carbocation, it's not a carbanion, it only has 1 unpaired electron on that carbon. So let's take a look at what we get. Well, radicals actually appear to be trigonal planar, sp2 hybridized, or we can consider them as being a shallow trigonal planar that quickly interconverts. So what am I saying here? I'm saying that you can consider the radical as being trigonal planar. You consider it as being flat, right? And we have an sp2 hybridized carbon, okay? Or you can think of it as a shallow pyramid, okay? You see how it's trying to show that it's very shallow and that they're interconverting rapidly. The take-home message from this slide for everybody who's in Chemistry 3101 is that you can always consider a radical to be trigonal planar in this class, okay? You can always consider a radical to be trigonal planar, and that's going to have some consequence later on when we get deeper into reactions and when we get into stereochemical considerations. So again, I repeat, our radicals, we can consider them to be trigonal planar. The carbon will be sp2 hybridized. All right, let's move on from there and let's talk about radical stability. Good news is that if you understood and can remember carbocation stability, that carbocation stability is pretty closely related to radical stability. Because even though radicals don't have a formal charge, they do have an incomplete octet, right? If you just analyze this carbon here, okay, here we have a radical carbon. So we could draw the carbon in even if we want to. That carbon is surrounded by 1, 2, 3, 4, 5, 6, 7 electrons. So it has an incomplete octet. Okay, well, what's the consequence of that? Well, the consequence is that radicals are going to follow the same stability trend as carbocations. Because why? Because they're electron deficient. So let's think about that. If this carbon is electron deficient, it is going to be stabilized by groups that can push or donate electrons towards the free radical. Well, how do groups push or donate electrons towards a free radical? They're going to do it by hyperconjugation. So hyperconjugation. Now, I'm not going to reteach hyperconjugation at this moment because we went over this in detail earlier on. But the bottom line is this, that the more R groups that we have surrounding our radical, the more stable it's going to be. Right? We saw the same trend with carbocations. The more R groups we had around a carbocation, the more stable it became. Right? So we go from a methyl to a primary to a secondary to a tertiary, which has 3 R groups all donating some electron density towards the radical. And that is why a tertiary radical is going to be more stable than a secondary, which would be more stable than a primary and more stable than a methyl. So again, you have to know free radical stability, and you have to know the trend that I have here on this slide. Very important. And we're just kind of laying some groundwork for us to understand what's going on when we look at radical reactions, right? You have to be able to assess a radical and say, well, is this one more stable than another? So on and so forth. Well, let's move on from radical stability and talk about bond dissociation energies and see if we can tie the two together. And I think we can. It says here that bond strength is inversely proportional to carbon radical stability. Remember that when we talked about breaking bonds, right? When we talked about bond strength, we could compare that to bond dissociation energies, which were the result of a homolytic bond cleavage, right? So when we're talking about bond strengths, when we look them up in a table, like all of these numbers here, these are bond dissociation energies. So what results when if we were to break any of the bonds in these molecules, right, the bonds that are highlighted, we would form radicals. Right, so it should make sense that as we go from the methyl carbon-hydrogen bond to a primary carbon with a carbon-hydrogen bond to a secondary to a tertiary, that the bonds, the carbon-hydrogen bonds, are going to get weaker and weaker and weaker. Why would that be, right? Let's take a look. If I was to break this bond homolytically, so here's one fishhook, here's another fishhook, what would I form? I would form a methyl radical here. Okay, and I'm going to skip the primary and the secondary just in the interest of time. And if we were to do the same thing here, what do we end up with in this case? We end up still with a carbon radical. Now it's surrounded by 3 methyl groups. And I think by now you should be getting the idea that a tertiary radical is going to be more stable. So again, as we have more substitution on our carbon, the carbon-hydrogen bond is going to be weaker. Something that we haven't really thought about earlier on, right? We haven't thought about this a lot in our class. In fact, if you look up the carbon-hydrogen bond dissociation energy in just a generic table of bond dissociation energies, they'll give you an average, right? They'll give you an average. So again, you have to understand the relationship between bond strength and radical or carbon radical stability and understand that this is an inversely proportional relationship. Okay, that the more stable the carbon radical that's going to be formed, the weaker the bond is going to be. Give me a thumbs up if you follow me on that concept. If you have any questions, feel free to stop me at any point. All right, good. Thanks, Moira. Yeah, good. We're just kind of, again, laying some groundwork here. We're still in the first section of the chapter. Excellent, excellent. Good. It's good to see that my students are following me here on a cold Wednesday morning. Well, let's move on from that and let's talk about free radical resonance. Oh boy, we spent quite a bit of time drawing resonance structures earlier on in this class, didn't we? We spent almost a whole chapter, looking at resonance structures, and they've come up repeatedly throughout the course. Well, just like carbocations or carbanions have resonance structures that show stabilization, radicals can also be stabilized by resonance delocalization. So if we take a look at this allylic radical, so this is a radical at the allylic position. I'll just call this would be called an allylic radical if I just wanted to describe this to somebody, right? We have our allylic carbon here, and it's got an unpaired electron on it. Well, we can use fishhook arrows to show the resonance forms. We have our resonance arrow here, and so we have 3 fishhook arrows that show the delocalization of that unpaired electron between this carbon and this carbon over here. Okay, so we need to know how to draw resonance structures of radicals. So let's take a look. It says the more resonance delocalized a radical is, the more stable it is. What's another way of saying that? The more resonance structures you can draw, the more stable the radical is going to be. Benzylic radicals are more stable than an allylic radical because the radical is delocalized over more carbons. Now, this might require some practice and for you to sit down and really think about this, but here we have a benzylic radical. If we have a benzene ring, okay, whenever you have an aromatic ring like this and you have any kind of, chain on it, this carbon right here, this is called the benzylic position. So that is why we call this a benzylic radical. It wouldn't matter if you had a long chain or if you just had, the one carbon here, okay? That's still called the benzylic position. So we start with our benzylic radical on the top right here, and you see that we have 3 fishhook arrows where we're forming a new pi bond here, and we're breaking this pi bond and we're putting an unpaired electron up on this carbon to give us the structure that we have right here. Well, we have 3 more fishhook arrows here, and let's see if we can draw what would be the result of these 3 fishhook arrows. So an approach that I like to take is start by drawing the skeleton and just drawing the parts that are going to be completely unchanged. So we'll draw these parts right here. You see that these 2 radicals are going to come together right here. So that means that I'm going to form a double bond at that position. So I'm going to have a double bond. Oops. I'm going to have a double bond right here. And then you see that one of the electrons from this double bond is going to end up on this carbon. So we have an unpaired electron right there. So now we've drawn another resonance structure. Can we draw more resonance structures? Yes, because we have a radical that's allylic to this pi bond that I have in the red circle here. So let's draw the fishhook arrows for that. We would form a new pi bond here, and then we're going to put a radical over here, and then we're going to draw the result of that. So let's draw our resonance arrow, and let's draw what this is going to look like. I'm trying to draw as neatly as I can here. So we're going to end up with something that looks like this. I'm going to draw the parts that remain untouched to begin with. We're going to form a new pi bond here, and we're going to have an unpaired electron over here, or a radical. And we can even draw another radical structure, can't we? Okay, now you see the big picture, and we can draw one more. So I'm going to draw one more resonance structure here. So I'm going to put this unpaired electron here. I'm going to put one of these ones here to make a new pi bond, and I'll move this electron up like this. And then I'm going to end up with this benzylic radical. So I'm going to be right back to where I started. I have all 3 of my bonds in the aromatic ring, and I have my benzylic radical right there. So here we have the resonance structures, or all the resonance structures of the benzylic radical that we started out with. All right, there's 4 of them. We have 1, 2, 3, and 4. You see that here we're back to number 1 again, so we have a total of 4 resonance structures. If you compare that with the allylic radical that was on the last slide, okay, so I'll just draw it out quickly. If you compare that to the allylic radical, wherein there are only 2 resonance structures, the benzylic radical is going to be more stable because here we only have 1, 2 resonance structures, whereas for the benzylic radical, we have 4 resonance structures. All right, so if you didn't quite follow me on the curved arrows there, this is something that you're going to have to practice. I've selected some problems from chapter 10 where Dr. Klein asks you to draw some resonance structures and get some practice in drawing those arrows. Well, let's talk about the stability of radicals again. We'll go right back to the topic of the stability of a radical and talk about how resonance stabilization can affect the stability of a radical. And then we're going to tie that into a bond dissociation energy. You're like, what do you mean exactly by that? Let me show you. What if we were to compare the tertiary carbon with the carbon-hydrogen bond, and we looked at this a couple of slides ago. What if we were to compare that to an allylic carbon-hydrogen bond or to a benzylic carbon-hydrogen bond? What's the consequence of the radical that's being formed being resonance stabilized? Right, if I form the radical from this, and I drew it a couple of slides ago, we got a tertiary radical that's not resonance stabilized. However, if I break this bond homolytically, I end up with an allylic radical. And if I break this bond homolytically, I end up with a benzylic radical. Well, you can see that although the tertiary was more stable than a secondary or a primary or a methyl, you can actually have an even more stable radical, can't you, right? And that's why the bond dissociation energies for the allylic and benzylic carbon-hydrogen bonds are even lower than that for the tertiary. Why? Because these ones are resonance stabilized. Resonance, okay, stabilized. And the reason the benzylic is even weaker is because it's got more resonance structures, or most resonance structures, okay? Give me a thumbs up if you just follow me on the concept, just on the concept of what's going on here. Of course, we're going to apply this concept, but it's an important concept for you to know as we move forward. Okay, good. Thanks, Patrick. Good. All right, great. Good. Very important concept to understand. Usually, by the time we get to this level of chemistry in Organic Chemistry 1, usually my students have a good idea of the knowledge of, have a good ideas about carbocations and hyperconjugation. It's kind of in their psyche at this point. And so tying it into bond dissociation energies and looking at stability of radicals is usually not that much of a stretch. Well, I'm going to borrow some more knowledge from that carbocation, from all the carbocations that we've looked at in Organic Chemistry 1. And let's talk about a vinyl radical. You remember that I told you that a vinyl carbanion, a vinyl carbocation is very unstable. We never see this in organic chemistry. We never see vinyl carbocations. And for the same reason, if you look at the vinylic carbon-hydrogen bond, it's really strong. Okay, it's got a really high bond dissociation energy. Why? Because if you were to form a radical from this, it's a very thermodynamically unfavored reaction because it's completely destabilized. So this is something else that you need to know, that since the vinylic radical has no resonance structures, it has no stabilization, it's going to be very unstable, and therefore the bond dissociation energy is going to be very high. So again, just like vinyl cations, we don't see vinyl cations in organic chemistry, okay? So we're not going to see vinyl radicals in organic chemistry either. If you draw a vinyl radical, you know you've taken a wrong turn somewhere. Well, let's take a break from learning new material and let's see if we can apply what we just talked about and answer a question. And this is not meant to be a mind-boggling or tricky question. It's just meant to test your knowledge as to whether you understand, if you can determine what is the most stable radical in a collection of different radicals that are all isomeric. So if we look at the top 3 and A, if we call them A, B, and C, could anybody tell me which one of these would be the most stable radical? Which one would be the most stable? Would it be A, B, or C? Yeah, thanks, Josh. Thanks, Chris. It's B, right? B would be the most stable. Why don't I just write above it? Call this most stable, because this is a tertiary radical. Could anybody tell me which one would be the least stable of all of these? Yeah, absolutely. You're all 100% correct. A would be the least stable. Least stable. And why? Because it is primary, right? C is secondary, so it's going to be somewhere in the middle. We can do the same thing with the one below. If I was to call these A, B, and C, you can see that B is going to be the most stable, right? Why? Same rationale. This is a tertiary radical, and C is going to be the least stable, right? Least stable. Why? Because it is primary. There we go. Okay. Don't, and I'm sure that nobody has done this, but don't confuse this. This is a secondary radical. Don't confuse that with a benzylic radical. Okay. That's something completely different. That's when we're looking at an aromatic ring. If you were to have that, okay, that's a benzylic radical. This is just a cyclohexane. This is just ethyl cyclohexane radical. Okay. So not the same thing. In fact, I should erase that. Okay. But every once in a while, you know, especially in the beginning of the class, you'll have students that confuse cyclohexane, benzene. All right, well, let's take a look and see if we can draw some resonance structures for some radicals. Now, these are, of course, the solutions to these are found in your textbook. If we start with C, you can see in C that there is a allylic radical right here. So we can draw some curved arrows for that, can't we? Right? We can form a new pi bond here and put an unpaired electron over here. And let's see what we get when we do that. If we do that, let's draw everything that's going to remain unchanged to start with. We didn't do anything with this bond. This methyl group is still here. Now we've got a new pi bond here, and we have an unpaired electron right there. Well, look, now we're set up again to draw another resonance structure because we have another allylic radical. Well, let's put in some arrows for that. So we're going to form a new pi bond here, okay? And we're going to form a tertiary radical here. If you don't like the way I drew that arrow, you could draw it like that. Either way, completely fine. And then we're going to end up with this resonance structure. Draw my ring. I'll draw the bond that is unaffected first. I'm going to have a new pi bond here. My methyl group is still here, and I'm going to have an unpaired electron there. Notice that this unpaired electron is not allylic here, and so that is the final resonance structure that we can draw. If we want to make this correct, we should draw square brackets around the entire thing, which denote that these are resonance structures. We can try the same thing here. You see that this radical is allylic to this pi bond, so we could start by pushing some arrows like this to make a pi bond. We put the unpaired electron up here. Let's draw what our resonance structure would look like. Okay, so we end up with our six-membered ring. We didn't touch this allyl group that's dangling off the side. We have a pi bond here, and we have our radical up there. So this unpaired electron is not allylic to this pi bond right here. And so that is the last resonance structure we can draw. So you don't want to fall into a trap of being like, well, I'm going to draw a resonance structure for every pi bond. No, not necessarily. Since that radical doesn't end up being allylic to this bond, you cannot draw a resonance structure wherein you would use that pi bond. And so those are the two resonance structures for this radical. Again, if you don't follow me 100%, you want to make sure that you take some time, get a piece of scratch paper, and practice drawing resonance structures. If you mastered resonance structures for carbocations and carbanions, then you should be able to, or generally speaking, I would say that students are able to master drawing resonance structures with unpaired electrons or radicals. Let's see if we can use some of our knowledge about radical stability and figure out what is the weakest carbon-hydrogen bond in each of the following compounds. So we got 4 compounds here, and this might sound like a weird question at first, but think of all the time that we spent this morning just talking about bond dissociation energies of carbon-hydrogen bonds. right? If we take a look at A, if we analyze this molecule in detail, you see that we have a pi bond here, okay? And we have all kinds of carbon-hydrogen bonds in the molecule, but we only have one that's allylic, right? We have this one here. This is an allylic carbon-hydrogen bond, right? If we break this bond homolytically, okay, if we break this homolytically, besides the hydrogen radical, we would also end up with a tertiary, draw it here as quickly as I can, you end up with a tertiary allylic radical. So this radical is tertiary allylic. And so that carbon-hydrogen bond is going to be the weakest of all the carbon-hydrogen bonds in that molecule. So this is the kind of approach that we want to take. If we look at B, zoom in here again. If you look at B, there are two allylic carbon-hydrogen bonds, aren't there? There's this one here. I know that there's two here, but we're only going to highlight one of them because we're just talking about carbon-hydrogen bond stability. Could anybody tell me which one would be weaker? Would it be the one in blue or the one in red? And it's not a trick question. Yeah, thanks, Josh. It's the one in blue, right? The one in blue, if we break that bond homolytically, we break the bond here, and we break this bond, then what do we end up with? We end up with another tertiary, it's like tertiary diallylic, isn't it? Right, because you have the radical here, you have a pi bond here and a pi bond here. And so, oops, I don't know why I'm drawing a gem dimethyl. Anyhow, what you end up with is something that is tertiary allylic. And you have two possible resonance contributors that you could draw here. Actually, there's more than that, isn't there? But anyhow, if we were to draw, what we would get from breaking the one in red, you'd end up with this. Okay, I'll just pencil it in here quickly. But this would be secondary allylic. Okay, they're both allylic, but tertiary is going to be more stable than secondary. Okay, let's take a look at the next one. The next one, there's only one type of allylic carbon-hydrogen bond in the whole molecule, and that's this one here, right? Why? Because this carbon has no hydrogens attached to it. So that's my only possibility, is the one that I have highlighted here, which would produce this guy. So you end up with this. You have your tertiary, or sorry, your primary. It's primary, but it's allylic. So we'll just put here allylic. So it's resonance stabilized. So I gotta move some of these papers off my desk. There we go. And the next one, let's see. The next one, the next one's a good one because we have an allylic carbon-hydrogen bond here, and we have an allylic carbon-hydrogen bond here. Could anybody tell me which one of these would be weaker? Would it be the one in blue or the one in red? And it is not a trick question. Mr. Dion hates trick questions. Yeah, exactly. It's the one in red, right? Because if I break that bond homolytically, I end up with an allylic radical. However, that radical, or that allylic radical, is tertiary allylic. So we end up with this. Oops, like that. This is tertiary allylic. And if you were to break this bond homolytically, you'd end up with something that's primary allylic. And so tertiary allylic is going to be more stable. So there you go. Something that you probably never, thought much about before, but now you can actually look at a molecule and just analyze, carbon-hydrogen bonds are ubiquitous in organic chemistry, but when you have the right kind of molecule, you guys will be able to look at it now and evaluate, hey, this carbon-hydrogen bond is going to be weaker than this one. What's the consequence of all that, right? It's something that we haven't talked about yet, but the consequence is going to be, well, if it's got a lower bond dissociation energy, it's going to be more reactive, right? So when we start looking at radical reactions, we have to be able to analyze which carbon-hydrogen bonds are going to be weakest, because those are the ones that are going to react first. Something really cool to think about. Let's move on to section 10.2, where we really get into the nitty-gritty of radical mechanisms. And you remember that when we studied ionic mechanisms, we looked at the proton transfer, the rearrangement, the nucleophilic attack, the loss of leaving group. And just like those ionic mechanisms, radical mechanisms have patterns that they follow as well. Although they're very different, they still have patterns. First thing that we're going to look at is the fact that radicals do not undergo rearrangement, right? If we had this carbocation, and if I asked any of you in the final exam, I said, is that going to rearrange? You'd say, yeah, that's going to rearrange. It's going to do a 1,2 methyl shift to produce, this carbocation. However, a radical is not going to rearrange to produce something that's more stable. But radical mechanisms follow 6 key arrow pushing patterns. And this is something put forth, I would say, by David Klein, the man himself, the person who wrote our textbook. And let's take a look at these 6 key arrow pushing patterns. We're going to start with what we call the homolytic cleavage. Now, we've looked at that quite a bit already this morning, but we haven't talked about what causes homolytic bond cleavages to occur. We looked at the curved arrows for them. But what you're going to see in this class is when we do a homolytic bond cleavage in a mechanism, that it will be initiated either by light, which we represent by h nu, Planck's constant times nu, okay, which again represents the energy of the electromagnetic radiation, or heat, for which we use the Greek symbol delta. So you need heat or light to get the reaction going. Once we've done the homolytic cleavage, we can do what's called an addition to a pi bond. And that's where we take a radical and we just add it to a pi bond. We break the pi bond and we end up forming a new radical. We can do a hydrogen abstraction, right? If the bond dissociation energy of the carbon-hydrogen bond is weak enough, right, we can break that bond using a radical. So we'll form a new bond between what was the radical and the hydrogen, and we end up left over with a new carbon radical. We can do a halogen abstraction. That's where a carbon radical will take on a halogen atom from either, from a halogen molecule, and you know what the halogens are, and we end up forming a new halogen radical. So that's 4. There's 6 of them. There's 2 more. The next one is an elimination. So that's where you take a radical and you do an elimination of a leaving group, so to speak, and you end up forming a pi bond. So we form a new pi bond in an elimination, just like an E2 or an E1, right? Those are elimination reactions. You always formed pi bonds. And the last one is a homolytic a coupling rather, and that's where 2 radicals come together to form no radical. Well, something that you might have noticed if you're very astute is that elimination is the reverse of the addition, which was the second reaction that we looked at, and the coupling is the reverse of the homolytic cleavage, which was the first pattern that we looked at. So we could say reverse of addition, which was pattern 2, and this was pattern 1. Well, patterns 3 and 4 are not the reverse of each other. They're not the reverse of each other, but 1 and 6 are, and 2 and 5 are, the way that they're laid out here. Now, I know I went over those kind of quickly, and the reason why is because the only way for you to master this is to really get into drawing these kinds of mechanisms. So the whole concept that patterns 1 and 6 and 2 and 5 are reverse of each other are shown here. This is a table that's comes directly from our textbook, where he shows, okay, these two are the reverse of each other, the homolytic cleavage and the coupling, then the addition to a pi bond and the elimination. Again, patterns 3 and 4 are not the reverse of each other. However, if you do a hydrogen abstraction, you could just do the reverse hydrogen abstraction going this way. So you could do a hydrogen abstraction and a hydrogen abstraction as being the reverse of each other. Same thing with a halogen abstraction. Anyhow, I don't know what the whole point behind this table is. As a teacher, I look at everything in the book and I say, what's the value of this? What's the value of that? And I guess, students do like patterns, and I guess, I do too. I mean, science students tend to like patterns. So if this helps you, that's probably a good thing. Well, let's take a look at these steps even closer here. It says the steps in a radical mechanism can be classified as either initiation, propagation, or termination. So these are 3 words that you want to have on your lips when you walk into the quiz on Monday. Initiation is getting the reaction started. Propagation is propagating the reaction, and termination. So I always think about them in that order: initiation, propagation, and termination. What's initiation? Initiation is when we start with no radical at all and we end up with a radical, right? It's just the production of radicals or a radical from a non-radical species. So here, if we do a homolytic cleavage of a halogen, we can produce a pair of radicals, right? Why is this initiation? Because we start with no radical here and we end up with a radical or a pair of radicals as our products. Well, what's propagation? Propagation is when you start with a radical and you end with a radical. So you start with some kind of radical and you end up with some kind of radical in the end. All of these, addition to a pi bond, halogen abstraction, hydrogen abstraction, elimination, you see what they all have in common. They all start with a radical somewhere in the reactants, and they all end with a radical somewhere in the product. So initiation, no radical to a radical. Propagation, you start with a radical, you end with a radical. Well, you can guess what termination is going to be, can't you? Termination is where you start with a radical and you end up with no radical, and that's absolutely correct. It's where you take two radicals, bring them together in a coupling mechanism, and you end up forming something that it has no radical. So initiation, propagation, and termination. These are patterns that you have to know when you're looking at radical mechanisms. Well, with some of that knowledge in mind, let's take a look and see if we can draw some fishhook arrows. So we're not really thinking about initiation, propagation, and termination, not in depth, but you can see that this is definitely a propagation step, isn't it, right? Because we're starting with a radical and we're ending up with a radical. Same thing here. This is also a propagation, right? We're starting with a radical and we're ending up with a radical. Anyhow, that's not really what I'm concerned with at the moment. I want us to see if we can draw the fishhook arrows to represent this reaction. So this is a pet peeve of mine, is that when you have a molecule wherein you have to break a bond and then they just draw the condensed structure like this, that is not good enough to draw the mechanism. Don't ever try to draw fishhook arrows like this. Okay, that's nothing. That's crap. Okay, and I don't take that back. Okay, so we have to draw the Lewis structure of HBr. What are we drawing? We're drawing a mechanism where we're going to form a new carbon-hydrogen bond, and we're going to be left over with a bromine radical. So in order to form this bond, to form a sigma bond, you can draw the two radicals or the two unpaired electrons as like meeting in the middle of nowhere, right? And that shows that you're forming a bond between this carbon and this hydrogen, right? That's what you're doing. And then you can draw another fishhook arrow to show the formation of the radical. Give me a thumbs up if you think you could do that. Or even if you're thinking, well, you know, give me a little bit of time to practice. Come on, man. Be reasonable here. Okay, cool. Yeah, so again, you can see that the arrows, so maybe I could write this or pencil this in here. Arrows connect in mid-air. I know it's not in the air, but I'll put that in quotations. To make a new bond. Okay, so these two are connecting in mid-air, but then again, that's showing the formation of this carbon-hydrogen bond. Okay, this one right here. Well, let's take a look at the next one. Again, it's another propagation step because we're starting with a radical, a bromine radical, and we're ending up with a radical here, a tertiary radical. Well, how are we going to do that? First of all, you should know that we need to form a new bond, don't we? We need to form this carbon-bromine bond. And so why don't we take one of the electrons from the pi bond and we're going to have it meet in midair with the unpaired electron from the bromine. Again, that is showing the formation of this bond. And then the other electron from the pi bond, I'm going to take it and I'm going to move it up here because I need to form this radical. Again, when the two fishhook arrows meet in there, this shows the bond being formed, which again is this carbon-bromine bond. All right. So again, you've got to be able to draw fishhook arrows for radical processes. Here, what's nice about these reactions is just like when we first started drawing curved arrows in ionic mechanisms, what was the first thing that we did? I gave you, or the book gave you, the starting material and the product, and it just said, can you connect the dots? Can you make the curved arrows? Right? And that's all we're doing here. It's giving you the starting materials. It's giving you the products and saying, can you connect the dots? Can you make, can you draw the proper reaction arrows? All right, well, let's move on to section 10.3, which if you look at the title of it, you think that doesn't look very interesting. The Chlorination of Methane. Okay. Before you make any harsh judgments, make sure you see the whole story before you're saying, oh, that doesn't seem exciting. It might not seem like the most interesting reaction if you just look at it saying, okay, if we take methane and we treat it with chlorine and a source of light, and if you've ever wondered, Mr. Dion, what do they mean by light? Do you mean the light bulb in the room, like just, or do you do chemistry with the lights out, or what? Well, normally when chemists do radical reactions and they need a light source, and I'm not being facetious, they will actually go get a big, like, high wattage light bulb and just shine it on the reaction flask. Like, you literally just plug it in the wall and shine it on, and the photons will help initiate the reaction. Anyhow, so you take methane, you treat it with chlorine and light, and you end up making methyl chloride and HCl. Well, this is a radical mechanism. And so we can use this very simple reaction in order for us to really examine the initiation, propagation, and termination steps. See if you can follow along with me here. The first step in the initiation is where we make a chlorine radical, right? When the Cl2, the chlorine, dichlorine, is exposed to light, it causes the homolytic cleavage to occur to form chlorine radicals. Now, before we move on, I don't want you to think, now listen to me very carefully here. If you're not awake, wake up for a second. Not every chlorine molecule is going to be broken apart into, tons and tons and tons of radicals. Some of the chlorines will be homolytically cleaved to give you some radicals, right? But you just need a few to get the ball rolling. Let me show you what I mean, okay? Once you've generated a few radicals, what can the radical do? Well, the radical is going to sort of start or kick off the propagation steps. The first step is going to be a hydrogen abstraction. So what do? We look at the carbon-hydrogen bond. We're going to break that bond to form HCl and a carbon radical. Now, again, remember, I told you that only some of the Cl2 molecules were going to be homolytically cleaved to form radicals. And so you're going to have a bunch left over. In fact, most of the Cl2 will still be intact, but the radical is going to react with another molecule, or a molecule of Cl2, to form the chloromethane. And then you've got a chlorine radical, right? You've got another chlorine radical. Well, if you're very astute, okay, and this is probably not the easiest thing in the world to do, and we're going to look at this in a second, but you notice that if you were to tally up these two reactions, right, what are the things that are the same on both sides, right? If we use a blue highlighter, right, you see that the radical is the same on both sides, right? The methyl radical, and so is the chlorine radical. And so what do? You have methane plus chlorine gives you methyl chloride plus HCl. Let's go back. Methane plus chlorine gives you methyl chloride plus HCl. I love it when a plan comes together. Okay, and we're going to look at that in even more detail in a couple of seconds. So I'm going to cross that out for now, but I want you to keep that in mind. Now, what's the termination step? The good news is the termination is, and I don't like to use the word easy in organic chemistry because it's not easy, but I'd say it's the easiest of all the steps, because in order for you to represent termination properly, all you have to do, my friend, is pick any radical that's in the soup. What have you got? You've got chlorine radicals. You've got methyl radicals. All you've got to do is show two radicals coming together. Any two radicals. If you draw a proper radical and another radical that's proper, that's part of the reaction mechanism, and you show them meeting on the street, and then they end up coupling to make something that's a non-radical, done. Okay? You're like, what? Even I could take the two methyl radicals and bring them together to make ethane? Yep, still counts. Okay? The whole point is that two radicals come together, they both get destroyed or annihilated, and you end up forming a new sigma bond, and you have no radical in the end. So termination is oftentimes students' favorite step, because they're like, I can take anything I want in the reaction mixture that's a radical, bring it together. Even if you only knew one of the radicals, you just bring two of those together and you make a non-radical, and done. Okay, so termination. So we had initiation, propagation, and termination. Let's go back to those propagation steps. Okay, let's take a look at the condensed structure of those. You notice that the sum of the propagation steps produces the net reaction. So here it is showing crossing out the chlorine radical and the methyl radical, and we end up with our net reaction, right? Which I told you was methane plus chlorine. And of course, you need either heat or light, one or the other, okay? And you make methyl chloride plus HCl. Well, what do you notice here is that you end up forming a chlorine radical. in the end, right? During the second step of the propagation. So what does that mean? That means that the propagation is a chain reaction, right? Because if you form a chlorine radical, it can go right back here and do another reaction with another methane molecule. That is why when you do this reaction, only some of the Cl2 molecules get homolytically cleaved to form chlorine radicals. You don't need to make that many chlorine radicals, okay? All right, there we go. Well, if we take a look at the chlorination of methane, and if you were to actually try to do this reaction, to just take methane, you treat it with chlorine, and you try to make methyl chloride, and of course you would produce HCl, but they left that out here. But if you have, you know, stoichiometric ratio of maybe 1:1 of your methane and your chlorine, the problem with this reaction is that once you've added a chlorine, the chlorine is an electron withdrawing group, right? And it actually is going to cause the other carbon-hydrogen bonds to weaken, and it actually speeds up the chlorination. So you keep chlorinating until you form methylene chloride, chloroform, and all the way to carbon tetrachloride. And so in order to make this reaction useful, you would just use a large concentration or a large amount of methane compared to the chlorine, and that way you can kind of mitigate it and cause the monochlorinated product to be the major product of the reaction. I don't know what I would ask you about that specifically, but it is something that I want you to be aware of. In order to prevent polychlorination, you would just use a vast excess of methane. All right, well, let's move on from there, and let's see if we can draw, what does it say here? Be able to draw mechanisms, as in Skill Builder 10.4. It says draw the mechanism for the following reaction: the chlorination of chloroform to produce carbon tetrachloride. So chloroform, right, is not only for kidnapping, okay, it's CHCl3, okay, and carbon tetrachloride, you should know how to draw carbon tetrachloride. Okay, when I first immigrated to the States, I worked up in Boulder at a company called Array Biopharma, which has now been consumed by Pfizer. And the guy who I worked for, or actually my boss's boss, still had a fume hood and was still doing chemistry in the lab instead of just sitting in a big chair calling the shots. And he had a whole bunch of different bottles of reagents. And being the boss of a company, you know, you can say or do whatever you want. And he had water, and he had that labeled like essence of life. And I don't know. And then one of them said chloroform, and it said for kidnapping. Anyhow, he thought it was funny. All right. Anyhow, so let's draw the whole mechanism here. So let's start with initiation. Initiation. Okay. So initiation, we're going to start with our chlorine molecule. Everybody should know how to draw the Lewis structure of chlorine. We'll draw the fishhook arrows for the homolytic cleavage. What do we get from that? We end up producing 2 chlorine radicals. There we go. So what happens next is propagation. So propagation, which is 2 steps, right? First, we have the hydrogen abstraction. Then we have the halogen abstraction. So let's start by drawing the hydrogen abstraction, which of course occurs first. So maybe I'll use black ink for this. So we'll draw the structure of our chloroform molecule. Draw the hydrogen over here. I'm going to leave the lone pairs and the chlorines out just to be quicker. We have our chlorine radical like this. We're going to abstract a hydrogen. So we're going to create a bond to make HCl. We're going to form the CCl3 radical. So let's draw that. We end up with our CCl3 radical like this plus HCl. Then what's going to happen is this radical is going to do a halogen abstraction. So now we've got, I'll call it X abstraction because in chemistry we use X to represent a halogen. So I'm going to copy this guy. Just copy and paste it right here. And that's going to react with another molecule of chlorine, Cl2. Remember, only some of the chlorine is going to be homolytically cleaved to give you radicals. So we're going to forming our carbon tetrachloride, and we're going to be left over with a chlorine radical. So let's draw that. We end up with our CCl4. I'll just draw the condensed structure. Plus, we end up with a chlorine radical like that. Okay, so there's our chlorine radical. Now, again, I'm not going to spend all my time, you know, canceling out everything here, but you see that the chlorine radical cancels, as does the carbon radical. And so what's the net reaction, right? Is that you start with CHCl3 plus Cl2, and that gives you CCl4 plus HCl, right? That's the overall reaction. Chloroform plus chlorine in the presence of heat or light gives you carbon tetrachloride plus HCl. Now, I don't have a lot of room left on here. I'll just quickly draw a termination step. Let's see here, termination. There we go. Let's pick 2 chlorine radicals and we'll bring them together. There we go, chlorine radical and another chlorine radical. And sometimes chemists will leave out the paired electrons, the lone pairs. So they'll just draw the radical just like this with 1 dot next to it, and that's totally fine. You want to do that. It's a good shorthand like this. And there we go. And then we end up producing, right, we end up producing chlorine. There you go. So there's termination, initiation, propagation, and termination. So make sure you're able to draw a mechanism like this, and you're like, well, it's not exactly like the ionic mechanisms, you know. No, it's a little different, but you want to make sure that you're able to draw an initiation step, a propagation, the 2 propagation steps here for a halogenation reaction, and the termination, the bringing together of 2 radicals to form a non-radical molecule. Okay, let's move on from there. Let's talk about radical initiators. This is kind of an aside, but it is important for us. If you're wondering, you know, what gets these reactions to move? You know, what initiates these reactions, these radical reactions? Well, I told you to, if you take chlorine and you treat it with heat or light, and again, I told you with the big light bulb, you can make a chlorine radical, but there are ways to enhance the reactions to get it to go faster. You can use what's called an alkyl peroxide, right? That's an old chestnut, because you looked at alkyl peroxides when we talked about anti-Markovnikov addition of HBr across a double bond, and we're going to talk about that in this chapter too. So that's a very weak bond, breaks easily. You can do the same thing with an acyl peroxide. So for an acyl peroxide, you would call it, you would just say R, CO2, and then, I don't know, O2CR, like that. Anyhow, nobody would ever draw it that way anyhow, so let me just erase that. I would always just draw it out like this. And the reason why the bond dissociation energy here is so low, okay, which one is going to initiate the reaction most readily? It's going to be the acyl peroxide. Why? Because this radical is resonance stabilized, right? You could draw this resonance contributor. So we'll put because resonance stabilized. And I'll let you draw the other resonance contributor with my curved arrows in here. So again, the answer is which one initiates the reaction most readily? It's going to be an acyl peroxide. All right, there you go. And again, the bond dissociation energy is the lowest of all of them. So I love it when a plan comes together. Well, let's talk about a radical inhibitor, things that can prevent radicals from forming. This is a very quick aside in our book. There's only 2 radical inhibitors that are discussed in our book. They are oxygen and hydroquinone. So you should know both of these, that oxygen and hydroquinone serve as radical inhibitors. What's a radical inhibitor? It's simply something that's going to react to the radical and stop the chain reaction from occurring, right? It's going to prevent initiation and propagation. So how do you, or what is a radical inhibitor? So oxygen is a diradical. And if you're thinking, well, come on, Mr. Dion, when I drew the Lewis structure of oxygen, you know, I thought it was this, you know. Well, if you go back to your general chemistry 1, you would have discussed how oxygen is a diradical, and that's why it is paramagnetic. It's attracted to a magnet. Anyhow, I'm not going to go into that right now, but the oxygen can react with 2 other radicals to eliminate them. Hydroquinone can also react with a radical. I have that shown here, so it can do a hydrogen abstraction, or undergo a hydrogen abstraction, I should say. It can actually undergo 2 hydrogen abstractions to form this fully conjugated molecule here called benzoquinone. Really, all you need to know from this section, I would say, is that O2, okay, so O2 and hydroquinone, okay, hydroquinone are radical inhibitors. That's it. Well, let's move on to section 10.4 and let's get into thermodynamics, right? A little Gen Chem 2 for your Wednesday morning pleasure. All right, so let's talk about how halogenation occurs And if you're wondering, what kind of halogenation do you mean, Mr. Dion? I just mean something like this, right? We talked about taking methane this morning and adding chlorine and forming chloromethane and HCl. Okay, well, how does that work in terms of thermodynamics? And could we use other halogens besides chlorine? Well, let's discuss that. So if we want to determine whether a process is thermodynamically favored or not, we have to look at the sign of delta G, right? When delta G is negative, the reaction is spontaneous, right? That's general chemistry 2. You spent a lot of time talking about Gibbs free energy. And we know that Gibbs free energy depends on an enthalpy term, delta H, right? The change in heat at constant pressure, and the entropy term, which is negative T multiplied by delta S. We did a similar treatment of delta G back in chapter 6, didn't we? Let me find out where it was here. Okay, well, if we examine the change in Gibbs free energy for different halogens, let's take a look at what happens. So first of all, in a halogenation reaction like this one here, the entropy term can be ignored. Okay, we can ignore that. Well, why? Well, we're starting it with 2 molecules and we're ending up with 2 molecules. And so the change in entropy is going to be so small that we're just going to ignore that term. And so that kind of simplifies it, doesn't it? Our delta G is going to be almost equal to our delta H. So that means all we have to do is calculate the change in enthalpy for a reaction, and that will tell us what the change in Gibbs free energy will be. All right, well, let's take a look here. If we examine the bond association energies for the reactions with fluorine, F2, right? F2, Cl2, Br2, and I2. Let's take a look at what would happen here. We have all the bond association energies laid out for us here. Of course, the bond association energy for the methyl carbon hydrogen bond is the same all the time. But for the halogens, you see the bond associations differ. The bonds that are formed, of course, are going to have different bond association energies as well. So what's the consequence of calculating the delta H of all these reactions? If you take a look at one, just for example, and I was just looking at my notes here for a second. Let's say we were to just examine the heat of formation, or the heat of reaction rather, with fluorine. So if we were going to do the delta H naught of reaction with F2, right? It's going to be the sum of the bond dissociation energies of the reactants, subtract the sum of the bond dissociation energies of the products. I hadn't planned on doing this, so I'll do it very quickly here. But you would have the bond dissociation energies of the reactants would be 435, right, from here, okay, plus 159 from the fluorine, subtract 456 plus 569. And when you tally all that up, you get your delta H for your reaction would be negative 431 kilojoules per mole. So it's very exothermic. And in fact, I can just tell you that this value is in fact so exothermic, or the reaction is so exothermic that it's not useful. Okay, when things are too exothermic, you can get things like explosions occurring. So I just showed you where this delta H value comes from for this reaction. So all the other delta H values are calculated in a similar manner. Well, if we look at, again, the fluorination, we'll say, let me write some notes in here. We'll say this is too exothermic to be useful. Okay, if you want to blow something up, maybe you could think about fluorination. But if you look at the delta H, which again is going to be approximately equal to the Gibbs free energy for iodination, you see that it's positive. So if it's positive, if it's endothermic, that means it's going to be an endergonic reaction and it's going to be non-spontaneous. So we'll say here, since delta G is equal to delta H, reaction is non-spontaneous. So that means the reaction is useless, okay? So what's the take-home message from this slide so far? Fluorination is too violent to be useful. Iodination just plain old doesn't work. So that leaves us with 2 reactions. We could either do a chlorination or a bromination. See that both of those are exothermic. They're not overly exothermic. So let's analyze those 2. Here on this slide, I just have a little blurb about, the fact that fluorination is too exothermic and iodination is too slow. Okay. Well, let's take a look at each of the steps of the propagation for chlorination and bromination of ethane. So we're taking a look at it from the point of view of ethane. If you look at the first step, the hydrogen abstraction, so first step is hydrogen abstraction. Again, this is first propagation step. You see that the change in enthalpy for the chlorination is -21. For bromine, it's +42. So that means the first step, or the hydrogen abstraction of with the chlorine, is exothermic, and for bromine, it's endothermic. If we look at the second step of the propagation, so this is the second propagation step, the halogen abstraction, both of them are exothermic. Now, you tally up both of those steps to give you the overall reaction, right? I've showed you how to do that twice today. You tally these up, right? You add them all together and you cancel this, right? And you get the net reaction. Well, if you tally up these numbers here, you end up with -117 kilojoules per mole. If you tally up these two steps, you get -50 kilojoules per mole, right? Okay. So this is for ethane. It's not for methane. I was going to go back and make a comparison, but it slipped my mind there for a second. Sorry about that. Anyhow, what's the take-home message here? What's my point? Okay, you're like, oh, Mr. Dion, it's just a bunch of numbers. I don't care. You know, just get to the important stuff. Well, I am at the important stuff. And the important stuff is this, is what's the difference between these two mechanisms? Okay, if you're kind of asleep, wake up for a second, because I promise you, you're going to understand this if you just hear me out. First step here, exothermic. Second step here, exothermic. In bromination, though, the first step is endothermic. The second step is exothermic. Now, if I was just learning organic chemistry like you are, and I remember the first time I saw this in lecture, I hadn't read the textbook. Okay, I admit it. I did that a few times in my life. And I remember the first time I saw this, the conclusion that I drew in my brain was bromination is going to be useless if the first step is endothermic, right? It's the activation energy is going to be too high for it to be helpful to hold the phone. Since the overall process is exothermic, there is actually an advantage to bromination over chlorination. Let me show you what that advantage is and why we have that advantage. So we look at the two steps, right? You have the first step is the first step is the hydrogen abstraction, right? Second step is the halogen abstraction, right? Same thing here. The first step is the hydrogen abstraction. Second step is the halogen abstraction. And again, we see that the overall process for both is exothermic, so it's spontaneous, right? Exothermic, but what about the first step? If we just focus on the first step for chlorination, right, we said that it was exothermic, but the first step for bromination is endothermic. And again, my first inclination was that, well, if the activation energy for bromination is so high, that means it's going to be slower, so it's useless. Not true, because even though it's slower, because it's slower, it's more selective. Now, do you remember the Hammond postulate? Okay, we talked about the Hammond postulate a little bit earlier on in this class. But the Hammond postulate is basically examining the transition state here at the top of the activation energy for the first step. The structure of the intermediate in this reaction right here, the structure of the intermediate in this first step here is more closely going to resemble the reactants, whereas the structure of the intermediate here in the first step is going to more closely represent the intermediate radical that's formed in the first step. And there's some very significant consequences of this. Let me show you what I mean. So let's say you had propane. Okay, this is just a molecule of propane kind of drawn in a funny way where we highlight all the different types of carbon-hydrogen bonds, right? We have 2 methylene carbon-hydrogen bonds, and then we have 6 methyl carbon-hydrogen bonds. So if you were to do a chlorination on this, okay? A chlorination on propane. It says there's 2 possible monohalogenation products. You can either put the chlorine where the methylene hydrogens are, or you can put them where the methyl hydrogens are. Either way, you do a substitution reaction. Now, what's the ratio that should be formed here? Since we have a total of 6 of these and 2 of these, the ratio should be 3-to-1. You should have 3 times as much this as you do this, shouldn't it be? But if you actually do the reaction, what you see is that's not what occurs. You actually end up with 60% of the 2-chloropropane and 40% of the 1-chloropropane. Well, why is that? If we take a look at that first step, okay, this is just the hydrogen abstraction. So if you're not following me, what you see in this yellow circle here is this part right here. Okay, we're just examining the first step in gross and gory detail. If you look at the first step, okay, look at the difference in energy between the two intermediates that yield the radical. Since the reaction is exothermic, the intermediates, okay, here are gonna more closely resemble the reactants. So that means the intermediates are going to have very little radical character, and so there's not going to be a very large difference between the energies of these two transition states. And so it's going to be discriminant because the secondary intermediate, or the intermediate that produces the secondary radical, is going to be a little more stable or a little lower in potential energy, but not that much. And so we see a little bit of an increase in the yield of the 2-chloropropane versus the 1-chloropropane. Now, what if we do the same treatment, but now with bromine? Okay, we're going to do the same thing. So if you do a bromination of propane, what you see is that it's much more selective. Even though it's slower, it's much more selective. And in organic chemistry, we're going to want selective reactions over ones that are indiscriminate. We get a 97% yield. Heck yeah, that's something I can hitch my wagon to. Why is it so much more regioselective? We can explain it using the Hammond postulate. Okay, since the first step, or the hydrogen abstraction in the bromination process, is an endothermic reaction, it means that the radical, or the intermediate that's formed, is going to more closely resemble the transition state. Now, since the transition state will be more sensitive, the transition state is going to be more sensitive to the nature of the substrate during bromination, right? Because again, the intermediate here, the radical, is going to more closely resemble the transition state. What is that? What's the consequence? Is that the transition state is going to have much more radical character, and the stability of a radical is important. Let me show you another way. Is that if we examine this transition state here during the halogenation using chlorine, so chlorination, the transition state more closely resembles the reactants, and so the starting material has very little radical character, and so it's not going to be nearly as discriminant as when we have bromination occurring, because now the transition state is going to more closely resemble the intermediate. It's going to be mostly a broken bond, and it's going to have much more radical character. We could just pencil this in here. More radical character. And what do we know? We know that a tertiary radical is more stable than a secondary, which is more stable than a primary. So if we compare the difference in energies of the transition states, you see that since the intermediates, okay, or since the transition state is much closer in energy to the starting material for chlorination, the first step in chlorination, that means that you're going to have a little bit of selectivity for the tertiary over a secondary over a primary, but not nearly as much as when we do bromination. Why? It's based on the Hammond postulate. Since the intermediates, okay, or the transition state, much more closely resembles the radical, and we know that a tertiary radical is much more stable than a secondary than a primary, that tells us why bromination is going to be much more selective than chlorination. Okay, so we did a treatment where we just looked at the activation energies for the hydrogen abstraction, and that explains why bromination is going to be more selective, and therefore it's more useful. Let's say you had isobutane. That's this molecule here on the far left. It's an isomer of butane. It's the only isomer of butane. Anyhow, we have isobutane. There's two types of hydrogens in butane, or isobutane, aren't there? There's this one here, and there's this one. Come on. There's this one here. Well, there's 9 times as many red protons as there are blue protons. So you would think that that would occur, halogenation would occur way more frequently where the red proton is, but you see that even when we do chlorination, it occurs much more at the tertiary position. Why? It's based on the Hammond postulate, right? And you see that bromination is even more selective in that we get basically 100% yield. We get none of these bonds breaking. And why? It's because the difference in energy of the transition states is going to be more, it's going to be a bigger difference in the energies of the transition states. Why? Because the transition states more closely resemble the radical intermediate that's formed. All right, there we go. Give me a thumbs up if you follow me on that concept. It's not the simplest concept that we ever look at. I try to lay it out as simple as I can. Maybe I over-explained it, but I certainly don't want to under-explain it. Okay, cool. Yeah, and I realize that we've gone over quite a bit of theory this morning. So next class, we're going to take more time to look at reactions. But before we get into reactions, this is going to be a very important slide for you, okay? Is that, yeah, fluorination is fast, but it's very non-selective, okay? Chlorination, intermediate, not very selective either, but bromination is much more selective. And therefore, I'd say most of the time, it's going to be way more synthetically useful, okay? This is about, 20 times more, right? 1600 is about 20 times greater than 82. And so, again, bromination is going to be the best process for us to use synthetically most of the time. Chlorination is really good to use if all the hydrogens in your molecule are identical. If they're all the same, then you can use chlorination. Okay, so what I'd like to start with at the beginning of class on Friday will be question 10.12. So make sure you take a look at this during the next class. Also, I just want to point out that we are skipping, just so you don't waste time on something that we don't cover, we are skipping sections 10.8, 10.9, 10.11, and 10.12. So you don't have to read those sections. You can, of course, if you want to, if you have an inquiring mind, but we are going to skip those sections. So we're going to cover 10.6 and 7, and then what else? We're going to take a look at section 10.13. So we only have 3 more sections to look at, and then the rest of the class on Friday we will spend looking at problems wherein we apply the concepts that we looked at in this chapter.